this is it. This is the last section of the book. This is chapter 20, section 3, graceful shutdown and cleanup. Yeah. Let's finish this. The code in listing 20-20 is responding to requests asynchronously through the use of a thread pool as we intended. We get some warnings about workers, IDs, and thread fields that we're not using in a direct way that reminds us that we're not cleaning up anything. When we use the less elegant Control-C method to halt the main thread, all other threads are stopped immediately as well, even if they were in the midst of serving a request. I see. Yes. We need to clean out this properly so that when we do things like Control-C, we don't cut somebody off in the middle of a request. We let them finish their jobs, and then we end it so they don't receive any new requests. So yeah, we need to gracefully shut down the server. Understood. Now we'll implement the drop trait to call join on each of the threads in the pool so they can finish the request they're working on before closing. Then we'll implement a way to tell the threads they should stop accepting new requests and shut down. To see this code in action, we'll modify our server to accept only 2 requests before gracefully shutting down its thread pool. So it looks like the way we're going to go about implementing the graceful shutdown is via drop, which makes sense. If you recall, drop is what happens when something goes out of scope. And I'm not exactly sure what the join on each thread will do, but stopping our channel from accepting new requests does make sense. So let's see how we go about implementing this. Implementing the drop trait on thread pool. Let's start with implementing drop on our thread pool. When the pool is dropped, our threads should all join to make sure they finish their work. Listing 20-22 shows a first attempt at a drop implementation. This code won't quite work yet. And we have a doesn't compile, but it might compile. Actually, no, it should compile, it just shouldn't work. So very confusing. But anyway, implement drop for thread pool. Function drop, mutable self. For worker in the mutable self workers, print line shutting down worker with worker ID. Worker thread dot join unwrap. Okay, so joining it is the way to tell the worker to stop. Understood. And this is all by its lonesome, so let's add that. Thread pool, and this is a trait, so we can just put it afterwards. First, we loop through each of the thread pool workers. We use reference to mutable because this self is a mutable reference, and we also need to be able to mutate worker. For each worker, we print a message saying that this particular worker is shutting down, and then we call join on that worker's thread. If the call to join fails, we use unwrap to make Russ panic and go into an ungraceful shutdown. Understood? Yes. Here is the error we get when we compile this code. We do get an error. Huh. So that thing was right? Yes, it was. I apologize. The error is move occurs, worker thread, join handle does not implement copy trait. Okay, yeah. Borrowing issues. Understood. But yeah, I apologize to this guy. There was an error. You were correct. This does not compile. The error tells us we can't call join because we only have a mutable borrow of each worker, and join takes ownership of its argument. To solve this issue, we need to move thread out of the worker instance that owns thread so join can consume the thread. We did this in listing 17-15 if worker holds an option thread join handle Instead, we can call the take method on the option to move the value out of the sum variant and leave a none variant in its place. In other words, a worker that is running will have a sum variant in thread, and when we want to clean up a worker, we replace sum with none, so the worker doesn't have a thread to run. Okay? So what they're stating here is that the issue is we're trying to join the threads, but the thread pool only has access to a mutable worker. But the thread pool does not have access to the actual closure, or the thread within the worker, right? In order to have access to that, we need to move the thread out of the worker so that join can consume it because of borrowing. The way they want to do that is doing the similar trick that we did in, I guess, 17.15, where we put something in an option and then we call that the dot take on it, called the take method, which then does like the switcheroo thing where we take whatever's in the option and replace it with none, and this, whatever this scope is, whatever took it, now has ownership of it. So let's see how we go about doing that. So we know we want to update the definition of worker like this. And yeah, thread is now option. Let's put that in there. Worker is right here. Now let's lean on the compiler to find the other places that need to change. Checking this code, we get 2 errors. Compiler-driven development. Run the compiler, see what the errors are. Got it. We get worker thread join. That's going to be an issue because it's now an option, so we need to check to see that something is in there first. And then we have mismatched types. Oh, we didn't change the parameter. Sorry, the argument. What's it called again? The signature. This function signature. So let's see what they have here with their errors. So they got this one, which we had, and they got this one saying that the type is wrong. Okay. So let's address the second error, which points to the code at the end of worker new. We need to wrap the thread value in sum when we create a new worker. Make the following changes to fix this error. Just wrapping it? I see. Just wrapping it will only return the worker. No, workers are going to still be returned. That didn't really change. Oh, yeah, the second error. I see. So they changed this to sum, and they had to do that because we changed this to option. Because this type changed, or at least this signature changed here. We need to make sure that we adhere to the new signature. So we need to make that sum. We can do that now. Make you. Kind of curious if the light bulb thing fixes it for me. No, I'm not sure if it does. Yeah, I'll just do it myself. Sum thread. Oh, do I have to actually state it now? Yeah, it looks like I do. Okay, yeah, because the name isn't the same. ID maps to ID, so it doesn't have to be changed, but some thread doesn't map to thread, naming wise. So that makes sense. All right. The first error is in our drop implementation. We mentioned earlier we intended to call take on the option value to move thread out of worker. The following changes will do so. So let's look at drop. For worker, immutable self workers, print the worker ID. If let some thread, making sure that some thread exists, worker thread.take. So if there's something to take, and then we thread.join unwrap. And when we take it, we gain ownership of it. So now drop owns it, and the drop is going to do thread.join, and then at the end of that scope, thread should get dropped. Technically, shouldn't worker get dropped at the end of this too? Yeah, everything should we're just dropping up everything. Worker should get dropped like here for each worker, and the threads, I guess, should be dropped here. Let's add this to our code. Drop right there. As discussed in chapter 17, the take method on option takes the sum variant out and leaves none in its place. We're using if let to destructure the sum and get the thread. Then we call join on the thread. If a worker's thread is already none, we know the worker has already had its thread cleaned up. So nothing happens in that case. Yeah. If it doesn't have anything to take, this gets skipped over. The next section. Oh, actually, we're not even done. Cleaning up is just the first part. We still have good ways to go down this document. Okay. Signaling to the threads to stop listening for jobs. With all the changes we made, our code compiles without any warnings, but the bad news is this code doesn't function the way we want it to yet. The key is the logic in the closures run by the threads of the worker instances. At the moment we call join, but that won't shut down the threads because they loop forever looking for jobs. If we try to drop our thread pool with our current implementation of drop, the main thread will block forever waiting for the first thread to finish. To fix this problem, we modify the threads so they listen for either a job to run or a signal that they should stop listening and exit the infinite loop. Instead of job instances, our channel will send one of the two enum variants. I see. So coming back to this paragraph, yes, we did some nice code with the drop implementation. The workers will be cleaned up. However, we still have the infinite loop running inside of the worker, and we haven't stopped that because that's still going to try to pull from the queue, our channel, and as such, that's going to just run forever. Yeah, so the way we're going to fix that is by sending we're creating an enum, and we're going to have two different types, right? We can signal new job, which is the current implementation. There's only one thing that gets sent, right? But we're adding a new one called terminate, and when we pass terminate through our send, and when our workers see terminate, they should exit out of the infinite loop. At least that's my understanding of it. So let's add this enum message, which at the moment does nothing because nobody uses it, so it's safe to put it anywhere. This message enum will either be a new job variant that holds the job the thread should run, or it will be a terminate variant that will cause the thread to exit its loop and stop. We need to adjust the channel to use values of type message rather than type job, as shown in listing 20-23. And how do they go about changing it? New job, job. Job, terminate, new job, job. Okay, I'm gonna have to keep this side by side and just go through it because that's just a very minor change in a lot of different places. It should be a number of different places anyway. Thread pool, job skipped, thread pool, message, new job. Technically speaking, oh, new job does take a job. Yeah, never mind, it's there. So job can stay. Send, message, new job, right here. Copy. This is in the execute. Instead of sending job, we send you. And it doesn't look like it likes that. I guess the enum new job isn't. Technically, it should be sized, right? Enum. I don't know. Send. Thread. Unwrap. We have a match here. Actually, to make this easier, I'm just going to copy and paste these new functions because they gave me the entire one. I don't have to figure out which lines changed. That's still the same error, so that makes me feel a little bit better. And then the worker, how did worker change? That's the same. We still have the thread, we're still moving. In our loop, we should have a match on message to check to see which one it is. And if it's new job, do what we're doing. If it's terminate, break, get out of the for loop, which makes sense. And they gave us all of worker, so we could just copy that over. To incorporate the message enum, we need to change job to message in two places. The definition of thread pool and the signature of worker new. The execute method of thread pool needs to send jobs wrapped in the message new job variant. Then in worker new, where a message is received from the channel, the job will be processed if the new job variant is received. And the thread will break out of the loop if the terminate variant is received. Which, yeah, we went over that in the source code. They're just going over this part. If new job is received, that variant, do the job. If terminate received, it break out. And the two places they said the chains were, I think, here. And was that one the second one? I'm not sure. I think it was that. But moving onward. With these changes, the code will compile and continue to function in the same way as it did after listing 20-20. But we'll get a warning because we aren't creating any messages of the terminate variety. Let's fix this warning by changing our drop implementation to look like listing 20-24. I see. So currently, with everything we did, one thing we haven't done is send the terminate variant to the workers, and that's seemingly next. So in the drop implementation, we have sending terminate messages to all workers, and then we're iterating over the workers. We're sending terminate to them because we still have access to sender because this is for thread pool. Shutting down all the workers, and worker, we're going to take access of the thread, and if anything is there, we're going to join it to say end. So the order of things, just to reiterate, is we send the terminate, which will break out of the loop, and if anybody is still working on a request, we want to make sure they finish that request but don't take any more, and that's where the join comes in. So that makes sense. Just go over our drop. And they said this should run now, so I should probably, well, let's check. I still get an error, and I probably forgot to change something. No, this is the new code, message.terminate. And I'm sending it, but it's not in a box or anything like that. Do they cover that? I don't know if they do. Let me see what they say first. We're now iterating over the workers twice. Once to send one terminate message for each worker, and once to call join on each worker's thread. If we try to send a message and join immediately in the same loop, we can't guarantee that the worker in the current iteration would be the one to get the message from the channel. Okay, that makes sense. All right, so what they're stating here is that they broke up the sending of the termination in one loop, and they put the joining of the thread in a different loop. And one of the reasons, seemingly the main reason why they did that, is if they join these into one loop, they cannot guarantee that the person that receives the terminate is the same person that they're going to try to join in one loop. And the reason that is not guaranteed is because even though that we're looping over the workers here, the order that the workers are in may not be the same order that the send or the workers are going to receive from the channel, because that's the two different avenues of execution there. One is a for loop that already has an order, and the other one is a channel with its own pulling order from the queue. To better understand why we need two separate loops, imagine a scenario with two workers. If we use a single loop to iterate through each worker, on the first iteration, a terminate message would be sent down the channel and join called on the first worker's thread. If the worker was busy processing a request at that time, the second worker would pick up the terminate message from the channel and shut down. We would be left waiting on the first worker to shut down, but it never would because the second thread picked up the terminate message. Deadlock. Ooh. So I explained earlier the reason why they didn't do it, but one of the consequences of if they did put everything in one loop is the possibility of deadlock, which they illustrated here. Yeah. Regardless, split it up, follow their instructions. We don't want a deadlock. To prevent this scenario, we put all of our terminate messages on the channel in one loop. Then we join all the threads in another loop. Each worker will stop receiving requests on the channel once it gets a terminate message. So we can be sure that if we send the same number of terminate messages as there are workers, each worker will receive a terminate message before join is called on its thread. Yes. They would want to make sure each worker terminates, as in stops receiving requests before we call join on it, and that's the way to guarantee it, by making sure by sending all your terminates first, and then in a different thread calling join or trying to call join on the threads. To see this code in action, let's modify main to accept only 2 requests before gracefully shutting down the server, as shown in listing 20-25. But before we do that, let's try to resolve this error thing, because they didn't actually mention it. So what is actually going on here? This is the line I missed. Sender, send message. And because of that, I'm having errors. And now everything should work fine, right? Yeah, everything is good. So yeah, that I forgot to change my sender to accept messages, which, my bad, I missed it. Alright, so now we're here. And we're modifying main so it only takes 2 requests. That makes sense. And then we can see the shutdown in action. So here's main. Only takes 2 requests. Now we can run it. You're the first request. You're the second. And then we're shutting down. Shutting down. Setting terminate message to all workers. Worker 3 got a job, executing. No more requests are coming in. Told to terminate, was told to terminate. Yeah. So one thing that's sort of cool is that because we're sending the message down the channel and the channel's behind a mutux, we know that everybody's going to wait until the lock of mutux is unlocked, and then they're going to just grab terminate. So that's pretty cool. One thing I'm not sure about is how to make sense of the ordering of this, but it's asynchronous, so it should be mixed up. And this was the shutting down line. Okay. Oh, I don't think I ever went through this. So yeah, to see what we did here is we have the bind, we have the 4 threads, we have the incoming take 2, as in we only try to take 2 of these, and once 2 of these have been taken, we exit out of this loop, and then we get to shutting down. So that's how we made it so that we only accept 2 requests. You wouldn't want a real web server to shut down after serving only 2 requests. This code just demonstrates that the graceful shutdown and cleanup is in working order. The take method is defined in the iterator trait and limits the iteration to the first 2 items at most. The thread pool will go out of scope at the end of main, and the drop implementation will run. Start the server with cargo run and make 3 web requests. The 3rd request should error, and in your terminal you should see the following output. So yeah, the output ordering is very different. I didn't make a 3rd request, but I could make one right now because the server has already been shut down. We should get that error. Yeah. But all in all, everything seemed to work the way I expected it to. You might see a different ordering of workers and messages printed. We can see how this code works from the messages. Worker 0 and worker 3 got the first 2 requests, and then the 3rd request, the server stopped accepting connections. When the thread pool goes out of scope at the end of main, it's dropped, implementation kicks in, and the pool tells all workers to terminate. The workers each print a message when they see the terminate message, and then the thread pool calls join to shut down each worker thread. So they walk through the output and the process that they went through for like the workers and the shutdown and the drop implementation. We kind of already went through that, so I'm not gonna, that's what happened. So here they're just reiterating the process of what this all did when we did the shutdown. Like after the 2nd request, it got out of the loop, got to the end, started printing shutdown, hit the drop implementation because we dropped thread pool, which then ran the other code and sent our workers to terminate message, and then joined the threads that the workers are working on, and then ended. And these are all the messages that printed out. Notice one interesting aspect of this particular execution. The thread pool sent the terminate messages down the channel, and before any worker received the messages, we tried to join worker 0. Worker 0 had not yet received the terminate message, so the main thread blocked, waiting for worker 0 to finish. In the meantime, each of the workers received the termination messages. When worker 0 finished, the main thread waited for the rest of the workers to finish. At that point, they all had received the termination message and were able to shut down. Congrats! We've now completed our project. We have a basic web server that uses a thread pool to respond asynchronously. We're able to perform a graceful shutdown of the server, which cleans up all the threads in the pool. Here's the full code for reference. And let me just change main back to what it was. Actually, wait. They didn't change main back. This is main for 2. I guess this is the end of the tutorial. So we can probably just leave it at that. But going through the code, we have a thread pool, which is our library that we implemented. They put in a hello crate. My crate has a longer name, but yeah. io.prelude, which I believe we imported so we have access to the result type alias for IO stuff. Standard library net TCP listener, so we can bind to a port and listen for incoming things. Streams, because we're passing streams to our handler. File server, file system, I'm not exactly sure what FS is for. And where do we use it? I'm forgetting, I'm skimping on it. Oh, we did it so we can read the string to file. Yeah, so I guess it's file system, and we did it so that we can read from the file system where we have our HTML code for the hello and the error. Thread, which we're very familiar with at this point in time because we used threading to process our request. Time duration, because we use our sleep endpoint, and our sleep endpoint slept for 5 seconds before it returned anything. And then here in main, we bounded to localhost 7878. I'm wrapped that there was an error, but that just makes sure that we're listening on that port for localhost. Created a new thread pool with 4 workers. We iterated over the incoming requests, and we then said take 2 because we wanted to figure out how our shutdown looked like, because we did the drop implementation for a thread pool. So this takes the first 2 requests and then gets out of this for loop and starts shutting down. Within the for loop, we have the stream unwrap, which is, I believe, is the TCP stream, and we're passing the stream to our thread pool that execute, which is a kind of soft wrapper around thread spawn. Well, not a soft wrapper, but a hard wrapper, because you have workers in there as well. But meh. Handle our connection. Handle connection took in the TCP stream. We had the number of bytes that we wanted to read for the header information, for the general input of the protocol and the route that HTTP person wanted from the stream, like the request. We hard-coded the endpoints that we cared about. The get one, which is on root, and this is the protocol. Make sure it was a get request. This is the page that they're requesting. Did the same thing for sleep. Let status line file name. So yeah, we did this here. If the buffer starts with, and the buffer is here, and we read that much from the buffer, and the buffer starts with get, we return the get page. If the buffer started with sleep, we slept for 5 seconds and returned the hello page. This is the hello page. The get page is the hello page. Else, anything else, we just returned the 404, which we gave them the correct protocol, or the status code. Said not found, and gave them the 404 page. So this tuple was then looked at here. So status and file name, status line and file name, which that was a refactor. That's how it got there. We used the file name to figure out which file we're going to read from. That gave us the contents of the page that we're going to respond with. And then we manually formatted our HTTP request response with the status line and the content. And I think there might have been something in between headers, which we just kind of skipped over because we didn't have any headers. Yeah, it would have been here. So this is the status line. Here would have been the headers in between these, and then comes the content of the page. Stream that right. We made sure we wrote out the response to bytes for the stream. The stream is the TCP stream, which is part of the request, and we flussed it to make sure that everything that we had in the buffer, in the stream buffer, got actually written to the buffer, so it got sent over. And that's how we handle that connections. Source libs implemented. I don't want to click that. We imported thread, imported channels, imported arc, and we imported mutux. Threads because we need threads to handle stuff. Channels because we need to be able to send our messages or our closures from the thread pool to the workers. Arc because we needed, or arc and mutux because we needed to be able to have our workers with their multiple workers, and each of them need to have a reference to the receiving end of the channel, which is it's single consumer. So technically speaking, you're only supposed to have one, but we put that behind a mutux so that only one channel at a time had access to the receiver. So that's how we got around that issue. We have our message enum, which either had a job, which is the closure that was passed in, or terminate, which meant shut down the worker. And messages were passed from the thread pool to the worker. We have our thread pool struct public, has a vector of workers and has access to the sender of the channel, and it sends messages, which is that enum variant, enum stuff up here with the two variants. Job, new job. Job is a type alias for box, and then the signature for the closure, which is dynamic. Capital FN once, which means it's a closure trait that's only going to be ran once, and also has to implement send because we're sending it from one thread to another. And static, which I'm not exactly sure why it needs to live that long, but this was also part of the thread spawn signature, and that's where we took that from, because we're pretty much just a wraparound thread spawn, so we need to be able to pass things to it. All right, thread pool, we have our doc comments here, which you could use cargo doc tag open or dash open, so it opens immediately, and it looks kind of professional. More or less, we wanted to state the panic, but this is more or less just for the panic because we didn't put documentation on anything else. And the reason why we have the panic is because new can panic, and that should be documented. Anytime you have code that can panic, the user of your code should know about it, especially if it's a library like this is. So the new can panic when you pass in 0 as the number of threads you want, because 0 doesn't really make sense as a number for threads. Anyway, moving onward, we make it panic by using the assert. We create the channel, so that gives us a sender and receiver. We then wrap our receiver in a arc and a mutex for the reasons mentioned previously. We create our workers vector with the specific size, so we don't have to, it doesn't have to like resize when we keep pushing to it. It's just a minor optimization. Since we know the size, we could just state we need a vector of this size. In this for loop, we create our workers, initialize our workers, and push it to the vector. When we do that, we use the ID from the for loop and pass that to the worker. And here we use arc clone to increment the reference counter for a receiver up one. And we're passing in just a pointer to the receiver. Then we return thread pool, workers, and sender. So we're just returning instance of thread pool because this is an associated function that returns a new instance of thread pool. Thread pool also needs to have an execute functionality on it, which is the wrapper for thread pool, wrapper for thread spawn. Here's where we take the closure. So we have our F, which F is bounded by the stuff we need for closures. The reason why we have the parentheses here is because even for an empty closure, we still need to be able to call it. So it's being called. We let our job equal a new box of F because closures are unsigned, not sized. And so we don't want to get compiler errors. We put it in a box, which then puts it in, gives us a pointer reference to it, and the pointer is sized, so that's fine. And then we send the job. Well, we wrap the job in a message, call it new job, and we send that down the channel. And the channel, as we recall, the receiving end of it is in the workers. Here we have our drop implementation for thread pool, which happens when thread pool goes out of scope. But again, we have a print line stating that sending terminate messages to all the workers, and we do that here. We do that in one thread. And later on, we're gonna try to take ownership of the threads that the workers own, and then stop them from doing anything, like wait for them to finish their current stuff and then say no more by calling thread.join. But the reason why we don't do that in one loop is because there is no guarantee that iterating over the workers and doing send message to will go to the same worker, because one is iteration of a set list which already has an order, and the order of that the worker is going to receive the message from the channel could be different, and that could result in a deadlock, which was stated in the somewhere in this page. But that's the reason why we separated it anyway. So shutting down all the workers happens after we send each worker terminate. And yeah, we loop over the workers. We print out which one we're shutting down, and then we try to take ownership of the thread that the worker owns. And we do that. We can do that because the worker thread is an option, and we can call take on the option, which does a switcheroo and place the workers portion of it with none, and then takes that ownership and brings it to this scope, which then we can call thread.join on it, and then it gets dropped. So coming down to the worker, our worker has an ID and a thread option, which we mentioned. Thread.join handles. Implementation of the worker, we have the new, which takes the ID, the size, so ID, which is usize, which is just a number, and the receiver, which we know it's an arc mutex channel receiving that sends messages down the stream, and it returns a worker for new. So here we come to the thread spawn part finally. Let thread equal thread spawn move because we're moving things into the closer, so the closer has access to them. Let message receiver dot lock dot unwrap dot receive dot unwrap. Let me see if I can recall the ordering for this. So arc is here, so that means we have direct access to the receiver. I forgot the term for it, but it allows you to call a method on arc, but it's actually being called on the thing that's within arc. So we're calling lock to try to obtain the lock for the mutux. We're unwrapping that because that could have an error, because the mutux could be in a poison state. And then once that is fine, we're calling receive on message, which is the channel portion. And channels could have errors because one or the other side could already be closed, and we're trying to receive something on a closed channel could cause an error, so we have to unwrap that. But if both of those work fine, then we just get the message. And then the message is an enum with the variant new job or terminate. So we have to match against that. If it's new job, then we print that we're executing the job, and then we run the job, which is the closer that got passed in. And then if it's terminate, then we break out of this infinite loop. And then here we just return worker ID thread, some thread, because thread isn't, this is an option, right? We could do more here. If you want to continue enhancing this project, here are some ideas. Add more documentation to Threadpool and its public methods. Add tests of the library functionality. Change calls to unwrap to more robust error handling. Use Threadpool to perform some tasks other than serving web requests. Find a Threadpool crate on crates.io and implement a similar web server using the crate instead. Then compare its API and robustness to the Threadpool we've implemented. So these are all great suggestions of things to do. I'm currently not in that type of mood, but they are actually pretty good suggestions on ways to improve on this and to further your knowledge on thread pools and web servers and like ground functionality of a web service. Moving onward. Summary. Well done. You've made it to the end of the book. We want to thank you for joining us on this tour of Rust. You are now ready to implement your own Rust projects and help with other people's projects. Keep in mind that there is a welcoming community of other Rustations who would love to help you with any challenges you encounter on your Rust journey. Oh, I have finished the book, and the summary is the shortest thing ever. Wow. One thing to note here that's sort of funny is they said you are now ready to implement your own Rust projects. Seemingly, that kind of implies that if you didn't finish reading the book, you're not ready. That's arguable. Well, we have reached the end of the video. If you like the video, hit like, subscribe. Outside of that, I need to find other things to do videos on. Peace.